This is the Python notebook that accompanies Chapter 7 of the Textbook Mining Complex Network. So this chapter deals with hypergraphs. We're going to be introducing a couple of new packages, namely the HyperNetX or HNX package and the XGI package, as well as a couple of Python functions that are included in the same directory as the notebook. One word of warning is that hypergraph or mining hypergraph is a pretty active research topic. So the packages such as HyperNetX, for example, are in constant evolution. So let's run those few cells. This is the path to the datasets and a function to compute the degree size correlation. So the correlation between the degree of no vertices and the size of hyperedges. Okay, so in the first part of this notebook, we're going to be illustrating a lot of concepts of HyperNetX and hypergraphs using a very, very small toy hypergraph. So to build the hypergraph, we're going to be using a list of edges, or it could be a set of edges also. Each edge is a set of vertices, a set of size usually two or more, but nothing prevents from having an edge of size one. For example, here we're going to have an edge that contains a single vertex. When I say edge here, I'm in this context, I mean also hyperedge is the same thing. So we're defining the hypergraph with this HyperNetX function where we're passing the list of edges, and the rest are mainly some attributes that we're adding. For example, every edge is going to have a weight of 1, and we're adding some colors and some size for the fonts that we're going to be using, etc. In the plotting, etc., etc. So this is our hypergraph. In this representation, this kind of rubber band representation, so the edges are represented as those kind of rubber bands here, and then the vertices are the dots. So vertex A, B, C, for example, are contained in hyperedge number 2. Okay, and here you see our hyperedge of size 1, which is hyperedge 6, which only contains vertex B. One important concept with hypergraph is the notion of a dual. So literally, the dual hypergraph is obtained when you exchange the role of the nodes and the edges in your hypergraph. So in this case, and you just build it in HyperNetX using this dot dual function. So literally, for example, our vertex B is now represented as an edge, and then the different edges in the original hypergraph, edge 0, 2, 6, and 7 are now represented as vertices. So this means that, the fact that this hyperedge B in the dual contains nodes 0, 2, 6, 7 is equivalent to the fact that in the original hypergraph, the vertex B was incident to the hyperedges 0, 2, 6, and 7. As we can see if we go back here, vertex B was part of hyperedge 2, 0, 2, 6, and 7. Okay, so that's a dual representation. There's also a bipartite representation, which is commonly used. So in a bipartite, here I'm just using the dot bipartite function, which will build in a networkx objects, which I can then pass to an igraph object if you want. You can just use networkx if you prefer also, but we've been using igraph, so I'm just passing this to igraph. And in this representation, you can see that your nodes and edges are all represented as vertices. And for example, this vertex B is incident to edges, 0, 2, 6, and 7. So those are the edges or hyperedges in the original toy hypergraph, and those are the vertices or the nodes. These are just a few uh, objects that I wanted to illustrate in HyperNetX so the dot shape gives you the number of nodes and edges. Those are the different nodes, the different edge, 0 to 7. The nodes are A to G. You can get the degree for every node. You can get the size of all the edges. That's something that is new in Hypergraph is now the edges have size. So they're not in graph. Remember, all the edges have size too, obviously. So here, that's one of the distinction is that we can have edges of different size. So two important objects and useful objects are the so-called incidence dictionary. So in the incidence dictionary, the keys are the different edges, and then the values are the list of all the vertices that are included in this particular hyperedge. So for example, edge 0 contains AB, edge 1 contains AC, etc., etc. There's also the notion of an incidence matrix. Sorry. So by default, an incidence matrix is represented as a sparse matrix. And here I'm also adding this index equal true flag. So it also returns the name of the nodes and the edges. But of course, it's, sparse matrices is usually what you're going to be working with if you're dealing with very large object, very large hypergraph. But in this case, I'm going to basically pass it as an array and then build a data frame out of it using the node or the vertex name and the edge names as the index and the name of the columns respectively. So just to be a little prettier, this is the incidence matrix. So for example, this vertex B that we saw earlier is part of edges 0, 2, 6, and 7. So there's a 1 in those respective columns. You could have different weights also, but we've set all the weight to as being equal to 1 in our case. And last but not least, there's a notion of a two-section graph. So you can reduce a hypergraph to a graph by using this two-section transformation. So basically, you replace each edge by the complete cliques that is formed by all the vertices in those edges. And there's a function in this hmod module in HyperNetX that allows you to do that. And you get something like this. In this case, there are different weights for the edges because nodes, pairs of nodes, can be part of a different number of hyperedges, for example. So AB and AC are part of, I think, two hyperedges. So the weight is a little larger than, for example, A to D. Okay, so important notion are the notion of S-walk and distance. So this is all taken from the book, so we're going to go quickly about this, but essentially, so we've already defined hypergraph and the dual, but just to review, the notion of an S-walk on the hypergraph is as follow. So it's a sequence of edges, E, I0, I1, etc., etc., such that the intersection between two consecutive edges in the walk is of size S or more. So that's what we call an S walk. And then from this definition, there's a notion of S distance between edges, which is the length of the smallest S walk between those. You have a notion of an S connected component, the maximum subset where there's an S walk between all pair of edges, S diameter. And you can also talk about wedges. So a wedge is a path from edge I to edge J, EI to EJ to EK. And then if this path is closed, so I to J to K back to I, then you have what we call a triangle. And so having the notion of S wedges and S triangle allows to define the notion of a clustering coefficient, for example, S clustering coefficient. So this is all on the edges. For the nodes, you can essentially do the same thing, but on the dual, and then you have the same notions for the nodes. Right, so one good exercise is to try to do, actually you can even do it manually, to try to do the following computations for the very small toy hypergraph. But for example, in the toy example, if we pick S equal 2, then the sequence of edge 1, 2, and 0 is an S path because the edge 1 and 2 share two nodes and the edge 2, 0 share two nodes, A and B. Okay, and in the dual, for the set of vertices DFE is an S path because nodes D and F are both incident to two edges and node F and E are incident to two edges. Okay, and there's another S path where S equal 2, which is formed by nodes C, A, and B. If you take S equal 1, then this will correspond to a walk on the two-section graph. But for S equal 2 or more, then this is a concept that really only applies to hypergraphs and is not, there's nothing equivalent for graphs. Okay, so we're going to be computing some distances, and a word of warning here is that an infinite distance between a pair of nodes mean that there's no S path joining those. And so we're going to see that for S equal 1, then this corresponds to the graph case, so the two-section graph case. But for S equal 2, then there's going to be some disconnected node pairs, disconnected components. Okay, so or S connected components, right? So let's have at it. So those are all of the distances between nodes, for example. And you can see that the distance or number of hops distance in the two section and the S distance where S equal to 1, those are the same thing. But if we go to S equal to 2, then there are some infinity values here, meaning that, for example, node A and node D are in different S connected component when S is equal to 2, right? And let's see what are those S connected component. So for the nodes, the S-connected component when S is equal to 2 are formed by A, B, C, D, E, F, and G by itself. And for the hyperedges, that's for the vertices, and for the hyperedges, you have 0, 1, 2, 3, 4, 5, and then 6 and 7 are isolated. So another important concept is the concept of line graph. So in the line graph, the nodes are actually the edges or the hyperedge in the original hypergraph. And then there's an edge between nodes in your line graph if those share at least S nodes, right? And you can, this is another way to see the connected component, building the line graph. So if we build the line graph of our hypergraph, and there's a simple function, get line graph, and you specify the value of S that you want, then you can see we get the connected component for the edges, 0, 1, 2, 3, 4, 5. This is what we had here. And if you do the same on the dual, then you get the same thing for the vertices. ABC is an S-connected component with S equal 2, and DEF is an S-connected component, and then G by itself. Okay, so there's a lot of text here, and this is all essentially the same thing as in the book, but we have notions of centrality measures that carry on to hypergraph using these notions of S distances. So, for example, S harmonic centrality can be defined because we have notion of distance between edges. And the same thing for betweenness, for example. We can define the S betweenness centrality because we have notion of distances. And in the case of centrality, it's going to be the ratio of the number of shortest S path between two edges, EJ and EK, that include an intermediate edge EI divided by the total number of S path between edges EJ and EK. So the same definition that we saw earlier for graph, but now there's the notion of shortest S path instead of shortest path. Okay, so for example, in the toy graph, when we had S equal 2, then there's only really two nodes that are on shortest path between other pairs of nodes. So there's node A that is between node B and C, and then node F that is between node D and E, right? So here, and that's what we saw in the connected component. And we can define other distance-based centrality, for example, closeness centrality, we're going to compute below. We can also define eccentricity. Eccentricity, remember, is the length of the longest shortest path from a vertex to every other vertices in the S line graph, in this case. So, yeah. So in this, by the way, yeah, I should mention, if we compute this eccentricity with S equal 2, you will actually, in HyperNetX, you will actually get an error because the line graph is disconnected. So here we're showing it for S equal 1. This is the eccentricity for all the vertices. And here we're computing the different centrality measures. So harmonic centrality, betweenness centrality, closeness centrality. And we're using a slightly different normalization than the one that is provided by HyperNetX. So this is why we're doing our own normalization here when we build the data frame. So let's see. You can see the only two nodes that have non-zero betweenness are A, and F, as we illustrated earlier. Those are also the nodes that will have the highest harmonic and closeness centrality. And then you have intermediate nodes, intermediate values, B, C, E, and D have intermediate values for the centrality. And then node G, which is isolated, has essentially zero value for all of those measures. Okay, so the next thing we're going to illustrate is the notion of hypergraph modularity and some clustering. So again, there's a lot of discussion in the book, but we're going to be computing different value of hypergraph modularity basically using different tau modularity. And recall, tau is essentially the value of the exponent that is used in the way we weight the edge contribution in the modularity. So for example, with strict hypergraph modularity, then the exponent is essentially infinite, and we only consider we only consider edges to be community edges if all of their vertices are in the same community. So C is the number of community vertices, and D is the size of the edge. So an edge is going to count as being part of a community if and only if all of its vertices are in the same community. And then all the way to a majority, which is as long as you have more than half of your vertices that are part of the same community, then you give essentially full weight, unit weight, and it's fine. All of those edges count the same. And then in between, you kind of have different values for functions, for weighting function, and this tau modularity, the tau correspond to the exponent that you use in the weighting function. In this case, you could be quadratic or cubic, for example. So the strict linear and majority functions are supplied in the HNX HMod module. And for the quadratic and cubic, we're going to define our own function, which is one of the thing you can do and supply in HyperNetX and supply your own value, for how you want to compute modularity. Okay, so that's a long explanation, but the function itself is pretty simple. So this is an example of how you would compute the quadratic weighting for the modularity. So C over D squared and cubic C over D to the power 3. Okay, so let's compute the hypergraph modularity for 4 different partitions of our toy graph. So A, B, C, G, and D, E, F, that should give us a good clustering. Okay, and then A, B, C together, but putting A with the other community, is not so good. If you put everything in the same community, that should yield a value of 0. And if you put everything in their own community, then that should give some small negative value. Okay, so we do the computation, and we can see that in this case, the values are quite similar, and the modularity is the highest in the first case, where the communities are nicely separated. And let's look at the 2 section. So this first case, A1 here, correspond to putting D, E, F together in a community, and A, B, C, and G together in the second community. Okay, and then the other values are as we explained earlier. So for example, the partition A3 gives you 0, partition A4 gives negative value, and partition A2 also gives value close to 0, slightly negative. Okay, so one thing we can do, and we're going to illustrate the concept here that is pretty, and a fact that is actually quite important when dealing with hypergraphs. So this is a 2-section graph, and it's always possible. We have a lot of tools to deal with graph, right? For example, we have this lead-in community detection algorithm that we can use. So if we build the 2-section graph, we can decide, okay, well, I'm going to use lead-in and do a clustering. And in this case, I extract, the 2 communities that we saw earlier. I'm kind of repeating this 100 times here just to do a timing, and you can see this is extremely fast, like 1.8 millisecond to do this like 100 times. Okay, it's a tiny hypergraph, or it's a tiny graph, but nevertheless, this is very fast. A hypergraph clustering algorithm that is discussed in the textbook is the Kumar algorithm. So if we apply Kumar algorithm which is included in the HMOD HyperNetX library, then so on our hypergraph, then we get, we get the same communities, the same clusters, but look at the timing here. Okay, so this is something to keep in mind. Working on this is a tiny graph, a tiny hypergraph again, so they're both pretty fast. But in general, working on hypergraph is much more difficult. It takes a lot more time than working on a graph, which is why this reduction to the two section is commonly used. On the other hand, you kind of lose the fact that what you really have under the hood are not, binary relation, but they're more complex relation. So keep that in mind, that there's always a trade-off between the speed. A graph usually you can analyze relatively quickly, for example, computing the partitioning, while for hypergraph, it's much more complex and any algorithm is typically going to be much slower, but on the other hand, the representation is contains more information, retains more information. Okay, so another concept we have in the book is this concept of simpliciality. So in this case, first we're going to compute this. Let's do this computation, and then we can discuss. So we see in the book we define this notion of simplicial ratio, which is how much more simplicial are you with respect to some null model. So in this case, you can see that we're slightly above 1. So we have slightly more inclusion of edges inside other edges than we would expect at random. And we also see that in this case, we have two edges of size 2 that are included in edge of size 3, and two edges of size 2 that are included in edges of size 4. But the inclusion of 2 in 3 is more surprising than the inclusion of 2s in 4. And one of this reason for that is simply the fact that if you have an edge of size 4, then there are many pairs, AD, AE, AF, DE, DF, EF. So just by chance, the possibility that one or a couple of those pairs of nodes appear in edges is higher than if you only have 3 vertices, so there's a smaller number of pairs of possible pairs that could appear as edges. And in the book, we also have other simpliciality measures. So in this case, for example, the simplicial fraction is 0. The edit simpliciality and face edit simpliciality, on the other hand, those values are between 0 and 1. So the other two measures are higher, indicating that there is some simpliciality here, some inclusion of edges inside other edges that happen. Okay, so this is probably a good time to pause, and we're going to be considering a larger hypergraph in the next part of this recording.